Now, with the alternating series test, we talk about the value to which that series converges, but we also talk about the remainder. That's defined to be the difference between the nth partial sum and the actual infinite sum, right? Since sometimes finding that actual sum is elusive and we don't have good tools of finding what the actual value s is, we want to ask the question, well, what's a good estimate for it, right? So we can get a partial sum out to a certain number of terms and say, well, that is an approximation of s, but how good of an approximation? So we can talk about the difference between the actual sum and the approximation for any convergent series, but it turns out with the alternating series, we have got a very easy way of determining an upper bound for the error, and that is the next unused term. So if I take my partial sums out to 5 terms, then that's going to be accurate within the size of the 6th term. Okay, so let me give you a graphical explanation for why that might be true. So in my favorite website, I'll pull up Desmos here. We're going to do k is our counter. We're going to go from k equals 1 to infinity. We can't really do that as far as I know, but I'll do 1,000, which will be good enough. And maybe my favorite sequence is the sum of the reciprocals, right? We know that the sequence converges to 0, but we also know that if we take the sum from n equals 1 to k of 1 over n, and we graph those in a series, then we can see that that one, as we've talked about before, diverges. It diverges slowly, but it definitely diverges. This partial sum follows the same basic curve as the natural log graph. All right? But now, if we turn this into an alternating series, as we've seen in the last couple of units, let's make this converging to a positive value, so make the first term positive. We know that this alternating series converges. Okay? So let's spend some time talking about this alternating series. Now with this scale, we can't really see it so well, so I'm going to stretch out the y-axis quite a bit. Okay? So let's make sure we understand what's going on here. This is the sum of the first term. This is the sum of the first 2 terms, so that's 1 plus negative 1/2. This is 1 plus negative 1/2 plus 1/3. This is 1 plus negative 1/2 plus 1/3 minus 1/4, right? The y values of these points are the s sub n, right? So we've got, I don't know, maybe it's 0.6 or so. It's not exactly 0.6. Oops, no, not at all 0.6, maybe 0.7. Yeah, maybe that's too big, maybe 6.9. Who knows? Well, I do, but I'm not going to say. Y is converging to a value close to 0.69. Okay? Notice that the S sub 1 is an estimate that's too big. And S sub 2, which is 0.5, is an estimate that's too small. And S sub 3, which is 0.83, is an estimate that's too big. And then we get to a too small, and a too big, and a too small, and a too big. But every time we take another step towards the convergence, we're getting closer, right? That was the whole, the value of the terms is getting smaller on each step. That was part of the alternating series test. So we can see that each of these values are getting closer and closer and closer. In fact, if I go from S1 to S2, if I go from 1 to 0.5, I've got to cross over this mystery value that's close to but not exactly equal to 0.69, right? So I've subtracted 1/2, and I went too far. Okay, well, let's try it again. Let's add, and I'll add 1/3. Oh, I went too far again. Okay, so I'm going from this approximation, I'm adding 1/3, and I've crossed the exact value when I add 1/3. Okay, so 0.5 is accurate within that next step's size. Okay, so this distance from down here up to here is 1/3, the size of the next unused term, but it is also bigger than the difference between 0.5 and the actual value to which the series converges. So that's going to happen each and every time, because every time we take another step, we pass the actual value that the series converges to, each step overshoots our goal. And that's where this n plus 1 comes from. The next step is always bigger than the error between the actual value and the current approximation. All right, so that's going to give us a range of values that we know our converging series is going to be in between. Okay, so how does that work in practice? If I have this converging series, I think we already did this one in the previous examples. We know that this converges. Now we're going to approximate it. S sub 6, we're going to go from n equals 1 to 6. So this is approximately equal to S, which is the original. So if I evaluate this, I don't want to do that by hand, so I'll go ahead and go into Desmos or a handheld calculator if you have one. N equals 1 to 6 of the fraction negative 1 raised to the n plus 1. N plus 1 over n factorial. I believe I'm remembering that right. N minus 1. That's not going to change anything though, is it? It's just because either way we're going to be starting with a positive value. Okay, so S sub 6 equals approximately 0.6319, or if we want an exact value, what the heck? We'll do an exact value of 91 over 144. All right, 91 over 144, that's exact. 91 over 144 is my approximation for S. So now the question is, how good of an approximation is this for S? Okay, so we know that R sub 6, the absolute value of R sub 6, which is equal to the difference between the actual value and the approximation, is always going to be less than or possibly equal to the next unused term. Notice I'm using a 7 here because we were using a 6 before. So what is this? Well, this is, well, it's 1 over 7 factorial. Okay, so that means that if I take my approximation and subtract 1 over 7 factorial, that's going to be the lowest possible value that S will ever be, could ever be, rather. And then if we add that same error, that's going to give us the largest possible value that S could be, based on the fact that this is the biggest our error could possibly be. All right, so we could go ahead and evaluate that if we want to. I'll go ahead and go back here, take that 91 over 144, go ahead and subtract 1 over 7 factorial, and let's see if we get a nice answer. It's not so bad. 199 over 315. 199 over 315. So S is in the interval 199 over 315. And then the maximum value, we'll just change that minus to a plus. And that gives us 177 over 280. 177 over 280. Notice we don't know what S is, but we do know that S is somewhere between that maximum and minimum values. And we can, of course, turn these into decimals if we would rather. But this is a kind of a nice exact sort of answer, so we don't have to deal with decimals.